I'd like to welcome everybody to this next presentation in the series Community of Practice webinars. The purpose of these webinars is to offer practitioners of concepts and methods related to risk-informed and performance-based approaches, we call them RIPB, a chance to share their knowledge and experience. I would expect that such practice is used for implementing nuclear technology and evaluating its safety. The Risk-Informed Performance-Based Principles and Policy Committee, RP3C, of which I am the chair, is part of the ANS and has been putting on these events for the past 3 or more years. Presentations and recordings of the events are available to the public at the ANS website under the tab RP3C. There are now more than 40 such recordings available. The purpose of RP3C is to help modernize ANS standards. The Nuclear Energy Innovation and Modernization Act, NEMA, of 2019, associates modernization with application of RIPB approaches. There is growing realization within the nuclear community that conventional prescriptive and deterministic approaches are not going to support increasing use of nuclear technology to play its rightful role for the benefit of society. Socializing alternative approaches could drive changes in industry and regulatory practices. ANS offers the COP files on its website to serve as a knowledge repository of the experience from a wide range of practitioners in the field. We hope that more people will use this knowledge base to speed up needed changes in the state of the art as well as the state of practice. These events are generally scheduled for the last Friday of a month. Today, we will hear from Mory Diané of Oklo. And I must mention that Oklo was one of the first advanced reactor developers to participate in this program of the Community of Practice. They had a presentation, that was about the third or fourth when we started in 2020. So I'm really grateful that Oklo has come back to this activity, and I'd like to request Mory Diané to get started. Mory, take it away, please.
All right. Thank you very much, Pat and Prasad. And we really appreciate being on the stage again to provide our views. Today, we're going to be talking about seismic design category and siting. My name is Mory Diané. I'm a licensing manager with Oklo. I support with, wearing several different hats, but one of them is with the building design and the seismic strategy for both on the regulatory side and also on the design side. We'll talk about some of the concepts and methodologies behind the white paper that we shared with the NRC on design categorization and siting. Before I get there, some of my background before Oklo has been with supporting new plant licensing, design, construction, operation with the US APWR with Mitsubishi, and also on the AP1000 with VC Summer and Vogel. I've also worked at Palo Verde plant and provided some regulatory and compliance support there. But my background is in civil engineering, and I'm a structural engineer. All right, let's move on make sure this is working. Can you all hear me and see my slides?
Looks and sounds great.
Okay, very good. Okay, so we'll go through an introduction. We'll talk a little bit about the technology that Oklo is looking at for the Aurora. We'll also talk about the regulatory overview. This will be the bulk of the presentation. So looking at regulations relevant to seismic design and site characterization, and also provide some insight from guidance, codes, and also standards. We'll talk briefly about the Oklo methodology, and then we'll go into takeaways and questions. All right. So Oklo is focused on providing clean, reliable, and affordable energy by leveraging our fast reactor technology as well as advanced fuel recycling technology. So some of the key points in our deployment strategy is the power cell model. So basically, Oklo plans to act as owner and operator of its plants, and we will sell power through power purchase agreements or other similar structures. For the technology, Oklo leverages safety by design and security by design approaches to produce inherently robust and secure powerhouses for increased worker and public health safety. The Aurora reactor facility that we are currently licensing produces 40 megawatt thermal, that's about 15 megawatt electric, to align with consumer demand and to allow for the rapid deployment of hundreds of reactors across the nation. With the size of the facility, this power level leads to a small radionuclide inventory and also a small powerhouse footprint, which also leads to enhanced or inherent safety similar to non-power and test reactors. So we've established that Oklo is designing inherently safe and simple advanced reactors for rapid deployment of hundreds of reactors. This warrants a re-evaluation of the traditional approach to siting used for large light water reactors, which involves a site characterization that is expensive and can last several years. The level of site characterization required for a large light water reactor is adequate for a facility that has a high dose potential in an accident scenario. However, for low dose consequence facilities, such as Oklo's 40 megawatt thermal reactor, those type of facilities can benefit from improved site characterization efforts. And we'll talk a little bit more later about the dose consequence. So Oklo's methodology was provided to the NRC via a white paper, which was submitted in November 2023, following several discussions, meetings that we had with them, and we also had some meetings after submitting the white paper. The methodologies provided in that white paper are focused on three key aspects. Basically, the goal is supporting the safe deployment of Oklo's reactors to those who want and need clean heat and electricity the most. The criteria is ensuring seismic categorization and site characterization is commensurate with the reduced risk of the facility while ensuring compliance with the regulation. And as a result, we want to be paving the way for a flexible approach to siting, supporting the low dose consequence facilities due to their small inventory, passive safety, and also robust design. And something I wanted to state before moving on from this slide is that there are precedents to what we're doing for the methodology that essentially that we presented to the NRC in starting with light water reactors, non-safety structure system and components, also for non-power reactors, research and test reactors, medical isotope facilities, which are all regulated by the NRC, and also DOE facilities, all which follow a much more streamlined site characterization process that is in line with lower, essentially when they have lower radiological risk, they have a streamlined approach, and this is adequate for their workers and members of the public. Okay, so the technology that we're working on really helps reduce plant complexity, cost, and also construction time. We are working on a fast reactor design. So I'm going to move on to the next slide to give you an example. In terms of fast reactors, we have over 400 years of operating experience across the world. Oklo specifically uses data from the experimental breeder reactor 2, that's EBR2, which produced about 20 megawatt electric and operated for 30 years by the Idaho National Labs, so from 1964 to 1994. The EBR-2 was a liquid metal cooled fast reactor, so it didn't use water as a coolant. This allows for the coolant to operate at higher temperatures and lower pressures than current reactors, improving the efficiency and safety of the system. So fast reactors use a fast neutron spectrum, meaning that neutrons can cause fission without having to be slowed down first, as they are in light water reactors. This allows them to use both fissile material and spent fuel from existing reactors to produce electricity. So we'll go through the regulatory overview. Again, this is the part that we'll spend the most time on. We'll take questions at the end after I go through the regulatory overview and the Oklo methodology. So we'll start with here with 10 CFR Part 50 Appendix S, which ensures that structure systems and components subject to the safe shutdown earthquake SSC remain functional. The SSC is the maximum seismic acceleration the safety-related SSCs can handle without failing. This is the seismic design basis accident. It is not a beyond design basis accident. Essentially, safety-related SSCs need to remain functional when subjected to the SSC. The next regulation is 10 CFR 123. That's the geologic and seismic siting criteria, which ensures that seismic site suitability through site investigations that account for uncertainty to allow for the selection of the ground motion response spectra, GMRS, and the SSE. So key difference here is the GMRS is the maximum acceleration that is specific to the site, while the SSE is the maximum acceleration that the design can withstand. The values do not have to be equal. But when they're not equal, the SSE must envelope the GMRS. And then finally, we have 10 CFR 5034, the contents of application technical information, which prescribes or has a threshold, a dose threshold of 25 rem that should not be exceeded. This accounts for mitigation. So when mitigation is applied, that 25 rem dose should not be exceeded. That's within 2 hours at the site boundary. And they are within a combined license application under Part 52. The corresponding regulation is 5279. And of course, early site permits, standard design certification and approval, and manufacturing licenses, they also have their corresponding regulations for this dose criterion. And essentially, we've also listed here some of the codes and standards that are typically used to achieve the focus of these regulations. So you have the safety-related SSCs needing to be designed to higher limit states. Typically, ASE 43 and ASE 4 would be used for a large light water reactor. And for the site investigations, including site response, you would typically refer to ANS 227, or for the uncertainty piece, which goes into a probabilistic seismic hazard assessment, you would look at 229, and there are other NRC guidance that we'll talk about later. And then on the dose, same, you would mitigate the dose through limit states that are prescribed by ASE 43. The limit states, we'll also cover that a little bit later, but essentially limit state C is a sustaining minor permanent distortion, and then limit state D, delta, is to maintain its elastic behavior, and then you have A and B, where A is collapse. All right, so here we wanted to talk a little bit more about the uncertainty piece. So we've quoted the portion of Part 123, 10 CFR 123, that talks about uncertainty. So we can see here that 123 wants to identify what the SSE is, but it wants to do it while accounting for uncertainty. And we can also see that there is a caveat where the probabilistic seismic hazard analysis is not a requirement. It is a choice that is provided because it says such as. So the alternative would be to use suitable sensitivity analyses. Through our discussions with NRC, the recommendation that was provided was to perform PSHA, the probability seismic hazard analysis, with a lower level SHAC, basically the SHAC is the Senior Seismic Hazard Analysis Committee that would be implemented to perform validation and peer reviews. So you have the different levels here that we showed here. You don't have to read through all of that, but there's level 1 through 3, and then I'm sorry, through 4. 4 is not shown on this table, but level 3 and 4 would be what typical large light water reactor would be performing, and what NRC had recommended for a lower dose consequence facility through our discussions would be potentially a lower level, maybe level 1 or level 2. The new regs, NRC new regs that talk through the SHAC levels are new reg 2117, and then also you have the more recent new reg 2213 that was issued in 2018 that goes over level 1 and level 2 in more detail. So a PSHA down to the level necessary to characterize a large light water reactor really increases the amount of investigations and evaluations necessary to confirm the site suitability and its seismic accelerations. Nuclear quality assurance NQA1 has to be implemented also. This increases the cost of the investigations. And the PSHA approach that NRC prefers is one that utilizes the SHAC process. The SHAC process, something to say about that is that it came about in the 80s. Based on what we investigated, it was related to an EPRI and Lawrence Livermore National Labs, LANO, PSHAs that were performed that had significantly different results for the same area. And since then, NRC has wanted applicants to properly capture all levels of uncertainty, aleatory and also epistemic uncertainties. We'll go through more slides on the uncertainty piece, because that's very important in terms of how to characterize it. So we have some quotes here from the DG 1410. That's the seismic guidance that reg guide that NRC is working on. It's currently draft for Part 53, which really opens the door for a lot more options for reactors other than large light water reactors, because as we will see in some of the next slides, the current regulation, Reg Guide 1.208, is really focused on large light water reactors of a high dose consequence. But the DG opens the door for potentially lower dose consequences, which would be handled through option 3, which can be handled through option 3. And we have a quote here. So this proposed option allows the use of a variety of performance and risk analysis methods besides a traditional SPRA to demonstrate seismic safety. SPRA would be the seismic probabilistic risk assessment. Typically, that's used to determine the classification, the safety classification, seismic classification of the structure, system, and components, SSCs. We also have within that guidance that option 3 would allow for a much more streamlined approach. So it says a combination of approximate bounding and conservative analyses and quantitative risk. So it's not prescribing an SPRA specifically. There's an alternative there. Also, the citing guidance, a reg guide that was issued recently, Reg Guide 4.7, has more discussions on uncertainty. It says the degree to which uncertainty needs to be considered in the siting analysis depends on both the reactor design and the details of the radiological consequence analysis. So again, it's tying the how much you need to do from a site-specific investigation, PSHA, SHAC, uncertainty quantification to the risk of the facility. What is the dose consequence of the facility? Again, we'll talk about that in the next slide. And there are more quotes from 4.7. For example, simpler design with relatively coarse assumptions might require less accounting for uncertainty, at the cost of design margin. So if you have a very conservative design, then you can reduce the amount of uncertainty that's needed. For example, there's another quote in 4.7 that we don't have here because I didn't want to overcrowd the slide deck. But it says, if not captured directly by conservatism in the analysis, then in that case, uncertainties should be established where applicable and quantified. So there are even cases where you don't even need to, go through uncertainty when your design is so conservative that it kind of basically envelopes. There's another quote that I wanted to share from a research information letter, RIL 2021-04, which is an NRC document that states it's a feasibility study on potential consequence-based seismic design approach for nuclear facilities, and it was issued in 2021. It says that the approach in this report can also accommodate codes other than ASC 43, which is what is typically used for large light water reactors, along with ASC 4. So it says the alternative here could be, it says such as ASC 7. It mentions the 2010 version. And it says that this would be for the design of low-risk facilities, and it has in parentheses microreactors or special systems or of relatively low risk, and regulatory framework for them is evolving. So these are all providing some flavors that will indicate that for a lower dose consequence facility, then a different approach than what's been used for large light water reactor would be possible. So we're now getting into the seismic design category. So the SDCs are a type of seismic classification that is assigned based on unmitigated dose potential for basically failed state of the safety-related SSEs. This would be following American Nuclear Society Standard ANS 226, 2004, which is the categorization of nuclear facilities, structure, system, and components for seismic design. And this was last issued in 2017. So here we're showing the different SDCs, so 1 through 5. Again, 5 is what Reg Guide 1.28 defaults to for large water reactors. And we have all the way down to 1, where 1 is a 0 rem, and then you have 5 with 100 rem dose. So under the ANS unmitigated consequence analysis process, those will be the dose that will be considered based on Appendix A. And you can see that this is unmitigated. However, the NRC dose, or the threshold of 25 rem that should not be exceeded, is mitigated. So it accounts for all mitigation. So you can see clearly here that if you are an SCC 5 and you are at 100 rem unmitigated, then certainly you need to mitigate that to get much below 25 rem, as far below 25 rem as possible. So in that case, limit state C or D that we talked about earlier would be needed in order to make sure that your deformation or distortion, you can maintain elastic behavior, or deformation such that the safety function of the SSE is maintained. But when you go all the way down to SCC 1 and SCC 2, then that's more akin to, let's say, a large light water reactor non-safety SSE basically would probably have these kind of similar dose consequences. So in those cases, you don't need to use limit state C or D. And why do you not need to use that? Is because unmitigated, you're well below the value that's needed for mitigated. Basically, if I have 5 rem on SCC2, I don't need to mitigate it because I'm already below the 25 rem. If I do mitigate it, then I'm going to be even lower than 5 rem. So that's the concept we wanted to share here, that essentially if your facility is comprised of only SCC 1 or 2, or if you have some SCC 1 and 2, then those SSEs inherently meet the regulation, this 25 rem mitigation. So if your facility just had those, then it should allow for much more streamlined way of addressing those lower SDCs. And again, this is essentially why the new draft guidance is opening the door for additional SDCs to be considered. This table here is from New Reg 2117, which talks about the PSHA and SHAC levels 3 and 4. This table goes over 3 levels of SDCs. I guess something I wanted to caveat here is that this table, it comes from ANS 229, 2008. The latest version of ANS 229 took out this table. However, it is still in the new Reg 2117. And you can see here the rationale is if you're at an SDC 3 level, you can benefit from a lower SHAC, a PSHA and SHAC level 1 or 2. And they have some conditions there. However, you can see that for SDC 1 and 2, they're not even listed in the table, which implies that if you're an SDC 1 or SDC 2, then technically you don't need to do a site-specific SHAC or PSHA. So, so really what would be recommended, to make sure that you are conservatively designing your facility. If your facility just has SCC 1 and SCC 2, then it will be to do a confirmatory site investigations with the use of regional seismic data. So basically confirming regional seismic data, which would come from the United States Geological Survey, the USGS. And the USGS performs regional PSHAs for the entire United States as part of their as part of their latest seismic hazard model. They performed a SHAC also following NRC guidance. I'm unclear as to what level SHAC was performed, but this comes directly from the report that they issued, the 2018 update that has the overview of the model and implication. It does have a line in there that they perform a SHAC also. And we'll talk a little bit more about the USGS later. There are also some flexibilities. So here we're looking at a slide from an older version of ANS 229. There are also some flexibility for lower SDCs with ANS 227 that looks at the site investigations were for SCC 3 and below. There are some flexibility there in terms of what might need to be done. So with this slide, we'll compare SCC 1, 2, and 5 to show that it wouldn't necessarily make sense to design an SCC 1 or SCC 2 to the level of an SCC 5 if your facility only comprises SCC 5. And the reason we keep bringing this up is because the current guidance that's available for power reactors under Part 50 and 52 points you to SCC 5 under Reg Guide 1.208, and that's why we keep trying to make the distinction between SCC 1 and SCC 2 for very low dose consequence facilities. So here we can see that the dose, we talked about the dose before with the 0 RAM all the way up to 100 and 500 RAMs for public and workers respectively. These SCCs are tied to different recurrence rates in terms of the earthquakes and also the probability of unacceptable performance in terms of failure. And the SCC 5 level has much lower probabilities, which leads to higher seismic events, and which would obviously be a worse consequence for an SCC 1 and 2. It wouldn't make sense to transpose that onto an SCC 1 and an SCC 2. So that was the key that we wanted to get out of these slides. So something else that we wanted to talk about here is that through our discussions, we are aware that NRC agrees that a facility could be comprised of only SCC 1 and 2. However, their position is that, at least that was communicated to us, is that a PSHA and SHAC is still needed, even if it's a lower level. But earlier we had discussed about how even a site-specific PSHA or SHAC should not be needed even for SCC 1 and 2. It should start at SCC 3. But the reason why NRC would want a PSHA and SHAC for these SCC 1 and 2 is because they have concerns with the USGS data that would be used for the design, that it is regional and it's not site specific. And based on their on part 100, they would like the information to be site specific, and that's some of the issues that they're having there. However, we can state that there are precedents even within Part 100 where PSHA, for example, is not mandated, or uncertainty, I should say, because it's PSHA is not mandated for power reactors. The uncertainty quantification is what's mandated. However, something we can note is that if you go into Part 100 in Attachment A, which is used by non-power reactors, research and test reactors, isotope facilities also use, medical isotope facilities also use it. Some of which sometimes have STCs that are higher than STC2, like for example, STC3. They're not required to do any PSHAs within their appendix. The requirements are very similar between Appendix A and 123, which applies to power reactors. However, one of the key differences is that in 123, you have the uncertainty, and then in Appendix A, you don't have that. However, if you end up with a reactor that has the same dose consequence as a non-power reactor, then it doesn't make sense to force apply this uncertainty requirement to that type of reactor. If it's really akin to it's similar in dose consequence to a research and test reactor, for example, there should be flexibility to allow for a similar approach to be provided. All right, let's move on. So we're almost at the end of the regulatory slides. So here we have RegAD 1.29, which establishes the Seismic Class 1, which is the Class 1 for safety-related components. And then you have RegAD 1.208, which kind of reconciles what a SC1 is compared to the STC. So it basically sets STC5 as SC1, and it does that through endorsing part of the methodology from ASC 4305, and it is used for site characterization of STC5 to select the SSC, as we talked before, or the GMRS, the ground motion response spectra. We also have NEI 1804, which is endorsed by the NRC. For non-light water reactors, design and licensing. It is an alternative that will certainly work for some advanced reactors. However, again, based on the RIL document that I quoted earlier, the research information letter. So this is not a quote from Oklo. This is a quote from the research information letter. It states that it is envisioned that some of the very small advanced reactors and microreactors with negligible off-site consequence can seismically design in accordance with ASC 7, and then it says LMP, which is a licensing modernization project per NEI 1804, would impose an additional and undue burden in the reactor design process. So essentially for those very small or low dose consequence facilities. So the reason I had highlighted RegAD 1.208 earlier is because even though RegAD 1.208 only points to SCC5 for power reactors, there is a pathway from RegAD 1.208 to the USGS data, and that's what we wanted to show here. So basically, it endorses part of the methodology from ASC 4305. So it hasn't been updated yet to ASC 4319, so it's still looking at ASC 4305. And so if a designer is stuck here and saying, well, do I need to design my very low dose consequent facility to SCC5 requirements? Then they would go to ASC 43 and see what else is there. And going to ASC 4305, they will note that for SCC 1 and 2, there is a direct pointer from ASC 4305 to ASC 7 and the International Building Code, actually. So maybe there's a missing arrow there, but it points you directly to, for SCC 1 and 2, you can use ASC 7 and you can use USGS data. There's an alternative path because ASC 4305 does not tell you how to, or does not give you the criteria for selecting the SDCs. As we talked about, some designers use SPRA for that. However, when you're using ASC 4305, it tells you go to ANS 226 for the selection of your STCs, and that's done through an unmitigated dose consequence analysis. Now, ANS 226, when you end up with STC 1 or 2, it points you to the IBC, International Building Code for the design of those. And the IBC uses USGS, or it also points you to ASE 7 if you would like to use ASE 7 instead. And of course, that also points you to the USGS. So ASE 7 is used for all types of facilities. It's used for mission critical facilities, commercial, industrial facilities, for example, chemical plants with hazardous materials, rad waste facilities use ASE 7, and they use it with USGS data. It is also used for some nuclear facilities, as we talked about earlier, that have SEC 1 and 2, so non-power reactors, research and test reactors, and some DOE facilities would use it. And also, this actually makes sense because the SSCs without any mitigation, as we talked about, they're unable to challenge the regulatory accident dose of 25 rem. So the accelerations from the USGS that the USGS generates are available publicly via the ASE 7 online hazard tool. Besides ASE 7, we talked about the IBC also relying on USGS data. And this really, having this ability to leverage commercial codes can greatly help expedite the deployment of smaller reactors like us. Like we're trying to deploy hundreds of reactors. So the current issue is, does a designer need to use, of course, reg guides are guidance, they're not regulation, but they're an acceptable guidance. If there are the only acceptable guidance, are they do they have to go through and use STC 5, or can they use something different? So if you imagine a transportable reactor that is meant for an emergency situation, and they have to license and they have to also go through lengthy site investigations. By the time they're done with that, the emergency has long run its course. So we need a more flexible approach to be able to rapidly license, perform the site investigations, and deploy these reactors, advanced reactors, including smaller reactors. So we'll quickly cover Oklo's methodology. This won't take too long so that we can open up for questions. So basically, the methodology that we have looks at two items. So the seismic design categorization, which is informed by ANS 226. Again, we don't adopt every single guidance in there, and there's a reason why we don't do that. We'll talk about it a little bit with those bullets. And then there's also the seismic site characterization, which is informed by ASE 7. So again, if something within the guideline does not make sense for the reactor, then we would have to adjust it accordingly. And that's why we have these as informed rather than endorsed. So for the seismic design categorization, we perform the unmitigated consequence analysis that is discussed in ANS 226. Essentially, we fail the SSCs that have a safety function, or that have a radionuclide release potential. And we assess the dose at the site boundary over 2 hours. And basically, this is looking at the dose that we're looking at here is the 5 rem and 25 rem. So 5 rem for the public, unmitigated, and then 25 rem for the workers, unmitigated. Those are from Appendix A of 226. However, there is also a qualitative requirement within Table 1 of ANS 226, which stipulates that for STC 1 and STC 2, you need to ensure that there's no requirement for public notification. Now, for that, we can't stay within ANS 226 and do that as unmitigated. We have to step out and look at what are NRC requirements from an emergency planning standpoint, because that's a little bit different now than seismic. We start looking at emergency planning, and emergency planning is governed by 10 CFR Part 5047 and also Appendix E. And those regulations would point you to the EPA Protective Action Guidelines and the dose thresholds that you have there, which is the 1 to 5 rem over 4 days at the site boundary. So we start looking at that. But the caveat there is that 1 to 5 rem is not an unmitigated dose. It is a mitigated dose. So it's a dose where you account for all mitigation. And that's why we have to step out of 226 to now address this dose. Now, which range, where do we sit in that range? We would look at a dose that is below the 1 rem over 4 days at the side boundary over 2 hours. The reason we would do that is because there are precedents, and they're also within the regulation, for example, 10 CFR 5160, which was recently issued via rulemaking. That regulation stipulates that if you are below the 1 rem, so you're below that lower limit of the tags, with your mitigation, your dose is below, then you do not need, you basically have an emergency planning zone that is that stops at your site boundary. And the significance of that is that no public notification is required in that case, because there are no prompt protective actions off-site. Basically, all of the actions are on-site, and they do not require public notification. So that's how we solve this with the analysis that we perform. So this now takes us to the ASC 7 process with the seismic site characterization. There we use the default site class. The site classes, as most of you know, with class A all the way through F, with A being hard rock and F being your liquefiable quicksand type of soils. So we would pick the default site class. ASC 7 has the defaults being class C through DE, and you would pick the one that has the worst, the highest accelerations. And then we also pick risk category 4. It's not required to pick risk category 4 because there are ways to, even for a mission critical facility, there are ways within ASC 7, section 1.5, that allow you, through a dose consequence type analysis with mitigation, to justify a lower risk category. So you would be able to justify a risk category 2, which would lower your safety, the margin that you add. Like in this case, we would add 1.5. We would multiply all of the seismic loads to 1.5. So we would use basically the highest loads that the USGS would provide. And basically, we would use these factors to determine a conservative design response spectra. So for the design response spectra, it is not site-specific. It's going to be a spectra that is that envelopes a portion of the US in order to cover multiple sites that we're considering. So this design response spectra DRS will be conservative. And basically, for each site, we then perform site investigations to confirm that the site amplifications and also to validate the USGS data that we're using through both the USGS data that would be the ASC 7 hazard tool would yield for the site, and then also that the DRS is conservative, envelopes what we're looking at based on the actual site investigations that we perform. And of course, we're noting here that for infrequent cases where the design is not bounded, further evaluations may be warranted to ensure that robustness against site-specific spectra is provided. And with these investigations, ASC 7 has a whole range of investigations. We would perform them all. However, ASC 7 doesn't require site response and PSHA for all sites. It would require it for site class F. However, they can be performed as needed. In our cases, we would perform all the site investigations needed in order to validate that the USGS data is in fact conservative. And also something to note is that even though we talked about limit states earlier, C and delta not being required, we would design our reactors to be robust. And this is how we basically include sufficient conservatism to mitigate any concerns with uncertainty based on what we discussed earlier. With that, let's go into the takeaways, and then I'm going to wrap up and let anybody who has questions ask some questions. So the methodology that we have in the white paper are appropriate for SCC 1 and 2. So One key factor that we have here is that following the ANS process that we discussed that mitigated those consequence analysis, really our ticket into ASC 7. We won't allow ourselves to use ASC 7 or the USGS unless we're able to validate that the SSCs are SCC 1 and 2. If we end up with higher SSCs, then we would have to look at a different methodology, basically. But what we're presenting is supported by precedents. As we talked about, several precedents use these methods or these codes and standards. It is also supported by industry code and standards, where we showed you the pointers to ASC 7 and the USGS. And based on our read of the regulation and what we demonstrated with the discussion earlier, this process would meet NRC regulations for these lower SDCs or low dose consequence facilities. And this really results in streamlining the site investigations, the cost, the time needed for those. And it also streamlines the acquisition of seismic loads, where you can obtain them from the USGS and then do a confirmation of that data. All right, this is it. I'm going to be just open the floor now to see if there are any questions, and I hope we still have sufficient time for that.
Thank you very much, Mory. That was really quite a sort of a sweeping, a perspective on all the issues related to the seismic categorization. We do have, I think, just one question right now in the chat, so let's take that up, Pat.
Sure. That one hopefully is an easy one. Just questioning what the title or perhaps the topic of DG 1410 is.
DG 1410, DG 1410 is the draft regulatory guide that is essentially the equivalent of Reg Guide 1.208, which is currently the regulatory guide that does that looks at the seismic design for large diameter reactors or current plants that are designed or licensed through Part 50 and 52. The DG is the reg guide for Part 53, which is still being worked on. And that's why it's still a draft guide. It's not been implemented yet, but there've been some draft that we've seen over the years. So last year, I think, was the last that we saw a draft. And I know that NRC is working through some updates that they will share with the industry on that.
Let's see, there's another question on chat that just came up.
Sure. So that's from our standards board chair, Andrew Sauter, and he asked if you can think of any of the industry standards in your area that could or should be improved via revision.
Yeah, so actually there is a process right now, and I think ANS is probably leading that process, where you are asking the industry to look at, a slew of guides, so mostly codes and standards that, in terms of like which ones are useful and what would you change, and we provided a lot of input on that. So for example, with the ANS 226, we don't want ANS 226 to be changed in a way where we would lose that ability to use ASC 7 like ASC 43 was changed, for example. Like I said, there's still a pathway, even 4319 still has a pathway through ANS 226 to get to ASC 7, but now for SCC 2, you can't get to there through 4319. In terms of reg guides, I would say Reg Guide 1.208, if that could be changed to have similar flexibilities as the DG that we talked about. The issue there is the DG is for Part 53. At one point, NRC was considering making it useful for Part 50 and 52 also, but based on the recent discussions, public meeting discussions that they've had on that, it is now just for Part 53. So part 50 and 52 folks, it's not clear, whether they can leverage that guide. I think there were some discussions about taking exemptions in order to leverage the options that are in that guide. So, this type of changes that are kind of ongoing and in draft phase, it is good for the industry to rally together and discuss with the NRC regulator and also the code and standard entities to make sure that there's alignment in terms of what is useful for advanced reactors, and really, from a technology, considering all kinds of technologies, right? Because like some of the changes, for example, we talked about with ASC 43 now maybe makes it a little bit more difficult for smaller reactors to use that as is for their SCC2s, because that requires PSHAs, site-specific PSHAs, and also SHAC for SCC2, which we talked about shouldn't really be needed.
Thank you. Andrew did just recognize that the group ANS is working through to get feedback from the industry for the advanced reactor community is the RSIC, Advanced Reactor Codes and Standards Collaborative. So just in case anyone hadn't heard about that, I did want to mention it. I'll go on to the next question, and just a recognition of your great presentation and questioning if you've received any feedback on your white paper, and if so, can you share that?
Yeah, I think general sense, I don't think we have even enough time to get into the details, but I did share some of the concepts that came out of that. For example, that NRC is amenable to a facility that is comprised of only SCC1 and SCC2. However, they would still like a site-specific PSHA and SHAC process to be performed for those. So that's kind of maybe the biggest takeaway there, where there is some flexibility that they would allow, where you wouldn't have to do a level 4, level 3, but you would still have to do a lower level. Now, if you're doing a SHAC level 1, it's a very minimal effort compared to a level 3 or 4. However, if it's not really mandated for, the risk, the dose consequence of an SCC2, for example, then why should you have to do that? So, we're working through, but definitely NRC is opening up and providing some flexibilities, but there's still additional discussions that are needed to kind of get to a final point.
Great, thank you. We've got a question from Jim August, and he's just questioning, what are some resources to learn more about Oklo's design technology and intended market niche? Jim did recognize previous community of practice presentations that are on the webpage and NRC submittals as well, but looking for input from you.
Yeah, I think on the kind of the business side of things, the website has a lot of information. Obviously, we're going public, and there's a lot of information on the website that's publicly available that goes through that, and so that's where I would point anybody who's interested in finding out more about how we plan, for example, to sell power, and which entities are we looking at to sell power to, for example. In terms of the technology, there should also be a presentation there. I remember from the last investor meetings that were held, there was a pretty detailed presentation there that talked about the technology, and that's also publicly available.
Okay. So go ahead, Prasad.
Sorry.
I was just going to say another shout out from Andrew, our standards board chair, just making sure that everyone on the call does go ahead and make sure that they provide any feedback they have on standards they need, revisions to standards, to whatever standards developing organization that has created the standard you use. Certainly use me as a resource if you're not sure. I'm happy to facilitate any of the needs that you do have. And then we do have recognition of a great presentation and just appreciation of the precedent you're setting with the choice of PSHA methods and the choice for STC.
Thank you.
Hey, yeah, I think we've seen a lot of very positive feedback on your presentation, Mory. I appreciate that.
Thank you.
Because we have just a couple of minutes, I do want to point out to you and others that ANS 226 is really, I think, the first risk-informed performance-based standard that was issued among the SDOs. You mentioned that the first version came out in 2004, and I've been told that it's been widely used. One thing that I have not heard is how this issue of mitigated versus unmitigated consequence can be dealt with using ANS 226. And in that, there is an Appendix C that specifically addresses that. You didn't mention that appendix. You mentioned Appendix A. Have you looked at Appendix C at all?
Yeah, Prasad, I did. I took a look at it, but we still ended up in the same place even after looking at Appendix C with the current process that we have of leveraging Appendix A and then providing justification for when we would go the unmitigated route for the emergency planning portion of it. But yeah, definitely we looked at it. What's in there, the prescriptions that are in there were very useful in helping us kind of confirm the strategy that we currently have.
Okay, that's great. That's good to know. Let's see. I think the only other thing on the chat was something from Jim August about, let's see, I'll let you read it, Pat.
Okay, really just Jim is questioning the timeline for your future program developments.
Program as in?
Jim, might you be able to clarify?
I don't know if you can hear me or not.
Yes.
Yeah.
Okay. Yeah. Where are you headed, or what are the things that you anticipate doing, let's say, in the next 2 to 5 years? Major milestones, any kind of future information that you can share?
Yeah, I don't have any specifics other than we're currently, we're working through the licensing process for the Aura, the design that I mentioned earlier, that is the 40 megawatt thermal, and we're having some good progress with that. And then also there is the the work that we're doing to go public. But as far as specific dates within the 5 years, I think stay tuned, and we'll see where we end, and we're all staying positive with with hopefully a good outcome for everybody.
Okay. Hey, thank you so much.
Mm-hmm.
Okay. Thank you very much, Mory. I think, if people have any other questions, you're most welcome to send them to Pat, and between my committee and reaching out to Mory if needed, we'll try to answer any questions you have. And I think we are right at the 4 o'clock mark. Pat, I think we can, thank people for their participation and attendance, and, all the best.
Definitely. And particularly a thank you to Mory for our presenter, and Prasad for hosting and taking care of everything. Thank you all so much, and have a great weekend.
Thank you.
Thank you.